Thanks very much, Anne. It's always a pleasure to interact. And thanks to Nutricia as well for the invitation today. So I'm guessing we're a little bit behind time, so I'll try and go through some of the basic information fairly swiftly. So today I'm going to talk about, I'm a basic scientist by nature. I'm neither a healthcare professional nor am I clinically trained, but I work in a clinical environment with lots of clinical colleagues. So and teach at a medical school, so I've got reasonable insight for a non-clinician, a non-healthcare provider in relation to that stuff. What I really want to talk about today is, so I'm just trying to figure out how this thing works. Just some quick disclosures, quickly. Is around muscle biology and how it interacts with nutrition, and particularly protein, as Anne alluded to. So muscle itself is an organ system, obviously. So most people think of organs, obviously, more traditionally, senses in kidneys, liver, brain, etc. But actually, muscle, of course, is its own ecosystem, and it's actually the largest organ of the body by mass. So in a healthy individual, it's around about 50% of total body mass. So, and it turns out that it's not just important in terms of factors including locomotion and movement, of course, which has been talked about a lot today in terms of things like sarcopenia, frailty, inability to get out of bed with chronic illness and such like. But it's also really important, actually, for reasons I won't go into today. It's a really important endocrine organ, and it's an organ that feeds other organ systems in times of need. So it's a huge reservoir of nutrients, in particular, of course, protein. And you find out, if you look in the literature across, if you look at a lot of the epidemiology, independent of the root cause of the clinical issue, is that muscle tends to really well link to health, and that's why people focus on this. And obviously, it's a key target organ in terms of nutrition and particularly protein. So we know that if it's compromised, increased functional limitation, falls, fractures, hospitalization, increased risk of disability and even mortality. And some of the basic data around things like even hand grip strength, would suggest that all-cause morbidity and mortality are linked to muscle function. There isn't really a chronic disease, including age or chronic disease, or even infectious disease, including, of course, most recently with COVID, that isn't associated with some muscle dysfunction. So this is just a loop for this audience. I obviously don't need to go into any detail about these conditions, but you've got rheumatic conditions, diabetes, obesity, cancers, of course, rapid wasting in critical care, chronic organ failure, heart failure, liver failure, kidney failure, or such like, respiratory diseases, and also infectious disease. So it's a really important target organ, and that's why nutritionists and dietetics and other biologists and physiologists are really interested in ways we can preserve it better to improve outcomes. So again, I've already talked about this morning, so again I'll flash over this fairly swiftly. This is just taken from a review which shows how dietary protein in particular is processed. I've already given a really obviously clear overview of those different steps, including all the enzymatic steps from mechanical breakdown within the mouth and some of the enzymes there, and then into the stomach, and then of course, which was talked about in great detail, into the small intestine, in particular where absorption, in particular of amino acids, occurs. And again, this was talked about this morning at the brush border in the area of the ileum, which I'll talk about a little bit later when we come up onto aspects of protein quality. And then, of course, what you have is the root of that is then into the large intestine, is that some of those nutrients, including amino acids that are either not absorbed or are fermented, for example, are excreted then into the feces. And of course, the other route is that, systemically speaking, if the amino acids get into the bloodstream, circulate to the tissues, they can be excreted through the kidneys in the form of urea and hence nitrogen excretion overall. The next stop at the end of the large intestine is, of course, the hepatic portal system. So don't forget that even if they make it to the ileum, they then have to translocate across the enterocytes and then into the portal circulation, where the liver will nick a large proportion of those amino acids, in particular the non-essential ones. And then it gets into circulation, and it can go to all tissues, or of course it can be diverted towards energy production or towards excretion through urea. So this is just an overview of what happens on a day-to-day basis in our muscle tissues, but actually in most tissues of the body. Put really simply, look at this wave, that we have a stable muscle mass throughout life typically, of course, unless there is a clinical or physiological challenge to that. If you wake up in the morning, typically what happens is that you have two processes occurring. MPS is muscle synthesis and MPB is muscle protein breakdown. So you have these processes that are constantly in flux. It's important to recognize that. It's not an ongoing process of equilibrium. It's one which is constantly in flux in accordance to the food that we eat and the dietary protein. So you wake up in the morning after an overnight fast. Essentially what this means is that your muscle is leaking out amino acids from the protein that it contains within them. So you're effectively losing tiny amounts of muscle. You eat food, and then what happens is this switches on an anabolic process within the tissue, and you'll notice two things. One is that the rate of synthesis rises. Two is that the rate of breakdown within the tissue slightly goes down. The net effect of that is an accumulation of muscle protein. Then in between meals again, this again starts to reverse such that the amino acids start to again efflux from the muscle tissue by virtue of protein breakdown. And this happens all the time throughout the day and throughout our lives. And if it remains equal and opposite, then everything's fine. If it doesn't, then that's when muscle becomes compromised as a tissue. We know the processes that drive this anabolic response, and I'm going to show you some of these now. Again, really quickly in the interest of time, it was started off by showing in the 70s or 80s that if you give people mixed macronutrients, that this drives anabolism in muscle. Then people refined that down and said, what are the main constituents driving that? So they went into eventually showing that the amino acids, part of the dietary protein, could do that. And then it was later showing that the essential amino acids, in other words, those amino acids that you can only derive from the diet and can't be made by the body, could drive that process. Then further got refined down to a cluster of amino acids, which I'll talk a little bit more about later, and then even a single amino acid leucine. So we kind of know what the driving force is behind this now, and it all centers around protein and the amino acids from which that are derived from intake of that dietary protein with eating. There we go. So what I'm going to show you now, just briefly here, is what happens when you ingest protein in the human body. If you just look, for example, kind of at the plasma essential amino acids here, this is a time course on this axis, and this is a concentration. Don't worry too much about this. The point is, this shows that if you look in between, this is like taking a blood sample at each of these time points. When you take on a bolus of protein, in this instance, I think it was around 50 grams of whey, which is quite a big lump of protein. Most of them normally would be taken in a single meal. What you can see here is that after a very brief latent period owing to the processes described previously, you see a rapid sort of plasma amino acidemia. This is the sum of all of the essentials. And you see it kind of stays up for 4, even 5 hours. So the availability of amino acids in the plasma stay high for quite some time in humans when you ingest in a large bolus like this. You notice that there's a slightly flatter outlook when you look at the non-essentials, and that's primarily because the liver will suck up most of those non-essential amino acids on first pass extraction. You also note, don't worry too much about the leucine here, you can see it follows pretty much a similar pattern to the essential amino acids, but if you look at the intramuscular concentrations of for example, the amino acid leucine, or any of the essential amino acids for that matter, you'll notice here that after, again, a short latent period, the concentrations in the muscle tissue stay up for 2 or 3 hours. So hopefully I'm going to allude to a little bit more as to what the relevance of that is in terms of muscle anabolism. What you find as well is that the muscle has will only take on amino acids for a very brief period of time. So most noticeably, what happens is, if you look at, this is skin here, this is an ultrasound image over a muscle bed, and you can see here that this is it. Once you infuse, it's a bit like, it's a contrast agent, a bit like if you were visualizing myocardial flow, for example. And you can see here that in a fed state here, this increased contrast indicates that increased blood flow due to opening of capillaries within the muscle bed to deliver the amino acids to build, as I've just previously described. One of the things that's interesting, if you actually are able to cannulate across a single muscle bed, the artery and the vein, so if you imagine that obviously in the arterial system, the amino acids are coming in, and then they're passing through the capillary beds, and then they're either going to be going in or they're going to be coming out of the muscle tissue. And what you find actually is, just to summarize what happens in muscle tissue, is if you look at what we call the AV balance, it means that in a fasted state here, the concentrations are higher in the venous than the arterial circulation, simply because, as I showed before, the amino acids are leaking out of muscle protein and you're losing muscle. When you take on the food, Here, what happens is the arterial concentrations become much more positive than the venous ones, as you'd expect, and then the muscle is sucking all of that up, and then around about here, about an hour and a half after eating, it stops. So it doesn't matter anymore if there's loads of amino acids floating around the blood. The muscle will not care. It's taken on what it needs over this brief period here. And after that point, any further amino acids circulating effectively are useless to the muscle and will go to other sources or to excretion. Then, if we then take a look at how this maps onto the temporality of the anabolic response in muscle, so this is the building process that we measure in humans, muscle synthesis rates. If you look at the graph here, this is basically the rate at which our muscles synthesize protein. In a fasted state, it's really quite low here. If you map, don't worry too much, again, this shows like 0.04, so this equates to about 1 to 1.5% per day. So in other words, after about 90 days, you've completely turned over your entire muscle mass within the body owing to the food that you take in. This is what the temporality looks like. You see a brief latent period. This is by biopsy. We repeatedly take chunks of muscle from people's legs, and we measure the incorporation of these traces into the protein pool. What we see is really simplistically, kind of after a short period, you see this spike, it goes up and it comes back down. This says that the muscle building period lasts for around about 2.5 hours in a human in response to any protein bolus that you take on. It doesn't last any longer, and it typically doesn't last any shorter. It just might be a little lower if you take on less. We carried on biopsying at the time because we didn't know how long this would last, and it turned out that, like I said, 2.5 to 3 hours. What was important in this observation too was that if we then looked at how this related to the availability of amino acids in the plasma or the intramuscular concentrations, once again, essentially, even though those amino acids are still highly available, the muscle has taken on all that it needs and the rest is all effectively wasted. So this opens up a huge area of how much protein do you need, what's protein, and getting onto things like protein quality. One other key feature, I think, which is an interesting one from a practical perspective, and that's what I'd like to share today, more some of the practical frameworks around what we find when we do these basic science trials, is that this is just a graph of protein synthesis response to food. In this instance, we gave 15 grams of essential amino acids as a bolus. What you see, again, latent period, it goes up and it comes back down again. If you then try and actually rescue this decline by giving more food, in this instance we actually gave leucine, which we know is highly potent, it does absolutely nothing. So basically, we kind of term this a tachyphylaxis, which is a pharmacological term for meaning that the system becomes refractory to a further response. So the practicalities of that is if you've given enough at a single time, it's useless giving any more because it's not going to work, at least in this setting. We also did some studies trying to understand more about how things like, as what's been talked about, things like, there are different, say for example, protein sources that have different digestive or absorptive characteristics. And one of the problems with trying to understand differences between sources like casein versus whey, so you have a fast absorbing versus a slow absorbing, is that they're slightly made up of different amino acid compositions. So to streamline this and to ask the question as to whether or not the rate of amino acidemia was important, we simply, took some free amino acids as 15-gram bolus or split it into 4. So the overall load is exactly the same, but the profiles look very different in the bloodstream. You can see here, just this illustrated here, 15 grams, this is all the sum essentials, it goes up hugely, it comes down. You kind of go, that looks great, and this one doesn't look so good. But actually, when you actually map it onto the growth response within the muscle, it didn't make any difference. So again, the muscle is rather ambivalent to the way that it's fed, in essence, whether it's drip-fed or whether it's fed as a bolus. One other important thing, just before I move on to some other characteristics around quality, is that I showed in one of the early slides that you see that obviously this waveform thing that I showed, which is an increase in synthesis, which is primarily due to the availability of amino acids. In fact, it's exclusively due to the availability. What we also see is a suppression of breakdown. You actually don't just see that on a muscle level, you see that in the whole body. So if you feed people and it's successful, then whole body protein breakdown will fall. So you'll effectively try and retain more nitrogen. And actually this occurs via insulin, not amino acids in humans. This is an experiment. It looks rather complex on the bars here, but so bear with me a little bit. This is a post-absorptive period. Again, this is a bit of an elaborate way of expressing exactly what I show in the waveform, in that you wake up in the morning. This is leg protein balance, by the way. Leg protein breakdown, leg protein synthesis, and then net balance. So net balance, if it's positive, you're gaining. If it's negative, you're losing. So you see here in a post-absorptive state, as expected, breakdown exceeds synthesis, and net balance is negative. What happens then is we gave the drug octreotide, which again was mentioned this morning, which stops the beta cells producing insulin, and we infuse insulin back under hyperamino acidemic conditions at a post-absorptive level, and then multiple up to pharmacological levels of insulin. Key thing is here, when we clamp insulin, what doesn't happen is a suppression of breakdown. So synthesis goes up, and net balance becomes positive, but breakdown does not change. If we allow insulin to rise, it drops. So the simple take-home message is that insulin is the driver of the attenuation of protein breakdown in muscle tissues, but also on a whole body level. So amino acids are important, and insulin is important too, in terms of anabolism of tissues. Okay, so then go back to the amino acid classifications. Again, you'll all be aware of this in this audience, but you've got non-essentials and essentials, and then you've got some, of course, conditional essentials, which may be important under certain circumstances. And then you've got the branch chains. So I'm just going to talk a little bit more about these ones here, because they seem to have rather a unique role, especially leucine in terms of muscle and other tissues in terms of regulation of anabolism. So here's an example. It's really quite surprising to see this. It was for me at the time, indeed, that when you give a human, a healthy human, a single amino acid, leucine, and then you measure this building response in the muscle, it looks pretty much the same as giving them 20 grams of high-quality protein, which is quite weird when you think about it. There are questions around, you will have questions, no doubt, around sustainability of this response in the absence of other building blocks, which is justifiable indeed, but the point is that from the perspective of evolution, it seems that the evolution has sort of adapted to be able to recognize that leucine is an indication that the cell that the animal has taken on food. So the cell is kind of blind to a lot of amino acids, but it sees leucine evolutionarily as an indication that there is food availability. And if there is food available, build. When there isn't food available, you don't build, you break down, and you create energy for other sources. Again, this isn't so relevant, but when we screen how the sort of pathways which trigger this response behave in response to the essentials, we see leucine really stands out. I'll just leave that there. What we do find is that in terms of things like metabolic aspects of muscle wasting, there's loads of stuff going on. Again, it was brilliantly shown this morning, the complexity of your different patient groups, how they may have varying degree of compromisation of physiology or medication or whatever interventions you're applying within them that might affect that. And we found with nutrition, these are a bunch of factors which, if you just focus on this one here, that have been linked, and this was done by, this little wee diagram was done by a really talented clinical PhD of mine years ago. And basically, we know that there are things like decreased consumption. Of course, there's behavioural aspects, satiation, etc. We know that there are aspects of altered splicing metabolism, probably now that the microbiome might also play a role in how, muscle wasting, and not just muscle wasting, lots of different conditions are impacted, and how nutrition interacts with that microbiome. I think that's just a work at the fairly beginnings at the moment. We also know that when the amino acids insulin get to the tissues, they're not quite as effective at driving those key homeostatic cues, which drive muscle maintenance. And we know that even when they get into the cells, they just don't quite work the same way for different reasons. So, once again, you've got this complex cascade of factors that may impact, the feeding response in terms of muscle physiology. Here's just a couple examples of what we would see typically if we look at very fundamental differences, let's say, between an older population and a younger population when we feed protein. And I'm just going to highlight this one to you here. This is the plasma amino acid profile if you look at young and old, and apologies that they're not that well delineated, but hopefully you can see that actually the older group is the squares, and the older group is the top line, and the younger is the bottom line. Now, anyone would think that this would mean that when you feed older and younger people, that greater curve in the old would be a good thing. But actually it's not. And the reason it's not is because normally what's happening is the younger people are much more efficient at peripherally utilising those for tissue protein synthesis than the older. So we know there is a problem there. And that's one thing which has led to people to think about how you adjust protein requirements, for example, in ageing, because the efficiency of utilisation falls. And that's just an example here. The graph on the right really just illustrates a slightly expanded version of what I showed earlier, in that if you feed, this is younger people fed bolus, younger people fed pulse, so again, where you have separate doses versus that whole single dose, and older people fed a bolus and older fed a pulse, you see that the feeding regime did not matter, but you see a low response, again, owing to that reduction in efficiency of utilisation. This is just shown here. This was a colleague in Canada, Master Prof Phillip, who generated this from his data. Quite simply just shows here that to achieve, this is in younger individuals, this is in older, to achieve the same anabolic response requires, as you can see here, around about 30% increase in the protein quantity per gram per kilogram of body weight. So we know that there is probably, in relation to metabolism as we measure it, we know there is a deficit, and we know that to a point, increase in the protein concentration quantity can overcome that. I'm just going to leave this in the interest of time. So what is protein quality? So this has a couple of meanings. For me, one is that the traditional protein quality terms, which you'll be more familiar with, which I'll get onto, would dictate that it's around limiting amino acids. When does an amino acid come limiting? I'll come back to that. But from a muscle perspective, the question is what's quality is what drives the biggest response. Simple. Doesn't matter what it is. That's what, quality at the level of the gut is irrelevant. It's what happens at the level of the muscle. So we did some studies, for example, where we, knowing what we did about leucine, this was actually in a group of older women. The graph on the right is just the one I showed previously. This is under fasted and fed state conditions. No temporal graph this time, just simple fasted fed block. We gave 20 grams of whey protein, or we gave an essential amino acid mixture of 3 grams only, which also contained 40% leucine, and we could not discriminate between that response. So from a quality perspective, at least from an acute metabolic anabolism, it didn't actually really matter whether you have a large protein bolus or you have a leucine-enriched smaller dose available. And it's not just us that's shown that; others have too. Again, from a colleague in Canada, he showed here that if you took 25 grams of whey protein isolate versus 10 grams of milk, but with added leucine such that the leucine matched and yet the protein quantity did not. You have 2 times the amount, the anabolic response on the rested, so just on the fed state conditions and alongside exercise, it didn't make any difference. So, quality can mean different things, I think, depending upon if you're looking at the level of the muscle versus other things which I'll get onto in just a couple of slides. Again, you're going to get the slides for this. Please, if you're interested in a broader look-see at how we did these dose responses and we expanded them out, please go read this paper, but I'll flash over that for now. Sorry. I mentioned about exercising and activity, so I'd just like, before I finally go on to the formalities of quality as it pertains to dietetics typically, one thing I will say is that we always observe is that the tachyphylaxis I mentioned before cannot be overcome by exercise. So that means that if you've contracted the muscles, then what happens is they remain sensitized to taking on those amino acids into protein. So again, show it really easy here. Forget the white bars for now, just focus on the black ones. Basal state here, you feed people, measure it over 2 hours. As I said before, it goes up. And then you measure it over 4 hours under rested conditions. And you see here that it comes down again. So what happens then if you layer exercise on top? This was people older ladies, just kicking, using a very lightweight exercise of one of the legs. So they took on the food, the protein, and at the same time they did some exercise for 10 minutes. And this is what you find if you do that. 2 hours it goes up as you'd expect, but it stays up by 4. And the muscle does this because it's remembering that it's been fed, it's had an energy stress, and what it's doing is effectively it's trying to adapt to that stimulus. And to adapt to that stimulus, it needs to remodel itself and use those amino acids in a more efficient way than under rested conditions. The same is also true in reverse when it comes to inactivity. This was with colleagues that we did, again, the colleague I mentioned before at McMaster, where we took individuals and we exposed them to reduced step count. Now, I know that in hospitalised patients that's a commonplace occurrence, especially in older patients, as colleagues tell me. So we exposed them to a reduced steps intervention, hypothesis being that this will negatively impact how the body responds to protein. And that's exactly what we find. So if you look here under fasted conditions, pre-intervention, before the step count, post-intervention, it goes down. So activity sensitizes the muscle to dietary protein, and inactivity desensitizes it. And this is what drives anabolism and catabolism of the tissue. So this is final bit, taking a little step back now into the GI tract from a dietetics perspective in terms of digestibility. So this is definition. A protein defined as the proportion of ingested proteins hydrolyzed into amino acids. Again, has been talked about ditripeptides, and then eventually, of course, into free amino acids via tripeptide peptidases. So final considerations in relation to this, like I said, moving away from the muscle, forget the muscle for now. There are many ways to assess this, which is a lot of competing interests, which I think is a challenge. Just to quickly highlight some of them. Of course, one of the classical ways, you can simply have an animal model, feed the animal, which animal grows fastest under different conditions. That tells you a lot about the protein quality in theory. You can look in the urine, so you can take a 24-hour sample, and you can say in response to different diets, how much nitrogen is excreted. And if you excrete less nitrogen, the retention of protein is higher in theory, for example. I won't touch on that, but if anyone wants to ask me, then please do. The classical ones, I guess, are the PDCAS and the DIAS, which I'm sure many, if not all, within this audience will be familiar with. PDCAS generally focuses upon the whole digestive tract and looking at effectively the sort of excretion of nitrogen components within the feces. The problem with that method is that those amino acids may be coming from other sources, the microbiota, there may be other processes. That's led to a more direct approach, where typically it's done in pigs, but it was also done in humans, where they stick a tube down into the terminal ileum and effectively sample as they take on whatever the test diet is. They then sample at that point of the ileum, and they look at the amino acids within them. And then they can basically say, well, compared to how much we need, depending on age, this particular feed provides you a DIAS score of this. So, a DIAS score would, as I'll talk in the next couple of slides, just very briefly, would be relating to something like, over 100 would be a very high quality protein. In other words, you have 100% of the dietary amino acids that you need, and not one is becoming limiting. And then as you go down, then you're getting more and more limited limitations. And the limitations are occurring because we have a human requirement of indispensable, and at some point, one of those runs out, as it were, before the processes and the needs are met. And that's the basis of DIAS. So just the last couple of slides. Again, I would just ask anyone who's interested in this. It's actually a really good review, this one in nutrients. Nothing to do with me, unfortunately, but really quite a comprehensive review of these approaches in terms of understanding more about digestibility. This is just to show you, it's quite a narrow, you can see here, 0 to 6 months, half a year to 3 years, now over 3 years. These are the amino acids, they're sulfur amino acids and aromatics collectively. And you can basically see here, it's rather meaningless just to look at this, but you can see in milligrams per gram protein it differs by age group, and that's what, the DIAS scores are effectively tested against. This is just to give some context in terms of food. This is a DIAS value again. Please just visit this review, it's a good one. And you can see here some food items or food groups down here. And these are the DIAS values in percent, which is calculated as ultimately as a percentage. And it also tells you, not that, again, it's that relevant, but maybe it could be because you could theoretically adjust for these rate-limiting amino acids. But you can see here that under different circumstances, you have different rate-limiting amino acids. The final slide I do have, again, is not, I wouldn't call it a plug, I am the senior author on this one, though, so maybe it is. This is put together by a PhD of ours. If you've got any interest at all in muscle biology and nutrition, especially as it pertains to protein sources, or musculoskeletal more broadly, then I would suggest you might consider having a look at this review. It gives a really kind of good overview of, the context of how different protein sources may impact musculoskeletal outcomes. So thanks. These are my concluding remarks, but I'll just leave them up and I'll be happy to take any questions.
Thank you very much, Phil. I think 4 words came to mind when you're going through that, and it's like protein, not so simple. But thank you for providing that very comprehensive overview and talking about quite complex mechanisms and quite a lot of data and really communicating that to our audience today. I had the privilege of doing a podcast with Phil where he talked about this topic, and I couldn't believe that actually he could get the messages across without any visuals. So it's really lovely to see it today with the visuals for our audio-visual learners. So thank you very much, Phil. Any questions from the audience? You answered sort of one, while you're thinking about it, I think you answered one for me. I was just thinking about, our typical patients with long-term conditions, inflammatory states, poor appetite, early satiety, typically they're eating, they're doing like drip feeding with food potentially, and often we do continuous feeding as well. And was I correct in that you said at one stage that you got the same results? They were in non-sick patients, were they?
Correct, yeah. So that's the caveat.
Yeah.
So we have actually been able to, that's not to say, so we have done, we are doing and have done nutritional studies in cancer patients in inflammatory bowel disease conditions to try and understand more about where, where the breakdown processes are occurring independently, even, if looking at the level, first of all, what happens at the level of the GI tract, and then, ideally the muscle. But as you know, one of the challenges there is biopsies.
Yeah.
Which is always a challenge. So the best we have is being able to understand more about, and I mentioned one thing I did touch on but didn't really talk about was the dual isotope method. The reason that's a useful one is that it enables you to basically see, just by sampling blood in any test meal you want. So it doesn't have to be, many of the other things will have to be a very prescriptive type of feed to understand this, or intrinsically level protein. You don't need that. So what we're trying to do is create more tools to minimally invasively monitor clinical populations. If that makes sense. That is a big movement in our lab.
And I think we've seen that in the University of Bath, where they do a lot with the athletes there. They're trying to look at, the quality of the muscle in their Olympic athletes by non-invasive methods, rather than biopsies, which is
it's a necessity to do this and to understand more in complex clinical scenarios. But one of the things is trying to get that balance between having the sort of the measures which may not be great in terms of outcomes, but having some more accurate ones but manageable ones as well. I think it's a real tricky balance.
Yeah, and obviously you've got the PROTASH study, which talks about 25, 30 grams of protein, in a dose from their recommendations. And here we are looking at results through a drip approach, trickle approach as such. Question from Vari at the front. Have we got a microphone handy? Thanks.
I can just shout.
Thanks, Michelle.
Thank you. I'm really particularly interested in the leucine, and particularly because we're seeing lots more people turning to plant-based diets, and there's less concentration. Does it make a difference where the leucines come from? Because this can be a problem for us trying to support particularly people that are choosing those different diet regimes.
So the leucine itself, if I'm answering correctly, the leucine itself, as long as it's L-leucine, it's the same leucine, if that makes sense. So it can be an insect leucine, it could be a plant or an animal-based leucine. The question becomes whether or not, again, if you go back to something like the DAS issue, and those grading systems, then, the quality of the protein may be deemed lower. In other words, leucine might not be the problem. And I think that's, they said, I'm certainly no expert in that area, but as far as I understand it, that's, one of the concerns is that you hit that limitation of running out of certain indispensable amino acids depending on the source.
Yeah. Thank you.
Yeah, Vicky, looking at the front there.
Thank you. That was a really interesting talk, and I was lots of thinking while I was listening to the talk as well. I was particularly interested on the effect of exercise with protein and examples that you used on older ladies as well. And I just think for the audience, I know a lot of you will be giving advice to older patients where sarcopenia and frailty is a risk. What practical things could you say to patients that actually would be helpful? Because in reality, a lot of these patients are often housebound, little mobility.
So this has been done, absolutely. I mean, I don't know how far it's gone in terms of translation, but I know there's a lot of movements a lot of activities towards trying to, understand is there a kind of, the word is, I hate the word threshold, and I always say the lifting weights, that's not realistic, right? But I know there's a lot of activities around chair-based exercises. I know that, for example, walking will recapitulate some of what I've shown. You will still require that extra, in small amounts still. From what we understand of it, people have done resistive band exercises again with a chair, and the results look fairly promising. It would, of course, there are some longer term trials to almost substantiate that to a point, but I think a lot of the guys a lot of people that worked before me in metabolism and nutrition kind of got to a point of saying, in certain states, you just have to have that contractile stimulus alongside the nutrition to maximize it. And there is just no question about that. It's not to say it won't work, it's to say that it will for sure have an additive effect in the right context, And it doesn't seem to have to be a high threshold either. I think there was a paper with 10 minutes walking in some instances.
Yeah. And it's interesting, actually, I work with physios and with palliative care, and there the physios, I've probably indoctrinated the physios about nutrition, but equally, there's a lot of crossover with the physiotherapy. And I think for me as a dietitian and other dietitians, the target group next might be physiotherapists to talk about how can we work together to make sure we address the function and the nutrition at the same time. And
I think even things like some of the sort of lesser knowns, I think, are passive versus active, muscle stimulation, as it were. So there's some stuff even with massage that is suggestive of a positive effect, and that's passive, or stretch and not active contraction. So I think there's stuff to be done there.
Yeah, and I think what you're doing is, like I say, laying that framework for how we do trials in the future that look at both functional outcomes in our patient population. Oh, sorry, Kainet, sorry, I couldn't see you. Are there any other questions? Oh, there's one question there, sorry. Any other? Put your hand up boldly, otherwise I might not see it. Yeah, one question from Kainet and another one.
I have a question following on to what was asked here. In terms of patients who are kind of housebound or bedbound and activity isn't really an option, is there a suggested time period of where you suggest that we space out the protein content?
So it's a great question, one I get asked all the time. And we did this study about 10 years ago, and I've still not published it, but it's coming. So it looks like, and I can only give you a vague idea, it looks like around about 4 hours there is a stimulation that's possible again. So we did a study, it's very complex, we did it in humans as well, so it's a long day. So you give a feed, and then you biopsy in a lot, and you're feeding. We fed after 1 hour, 2 hours, 4 hours, and we biopsied. And the only time we couldn't go any further, but the only time we see it creep back up is around about 4 hours. And again, it's not my work, but there is a colleague in the Netherlands who's quite an advocate, have published quite a lot on nighttime feeding, because it's the biggest, longest post-absorptive period, isn't it, overnight? So the idea is that, if you can only use a finite amount, and again, this has fueled distribution trials, right? Of, for example, in older people, typically it would be reported that it's not an even intake of protein for a day. It's heavily skewed towards dinner. And is that optimal? And I think there's still, the jury is actually out. Theoretically, from some of the work we've done, it would be the case. So I think the idea is that even distribution, but again, I don't think it's not been that robustly shown. But again, the overnight protein does stimulate protein synthesis, as you would probably expect it does, and therefore that's the longest post-absorptive period. Why not use it?
So I could effectively advise patients to take their supplement just before bed, and that would have a better.
Yeah, because the clock, as it were, the circadian clock doesn't, as we know it, affect responses to feeding. It might do in theory. There's quite a lot in the press about how it affects his maybe response to exercise, but in terms of protein, nighttime protein works in terms of muscle.
Thank you, that's really helpful.
There's one question. Any other questions? There's one in the middle there. Yeah.
Thanks for your talk. I was hoping that I've understood it correctly, that if you've got that smaller amount of protein, but with the leucine enriched, that you still had that beneficial effect on muscle growth. But whether there are any, I'm just thinking for patients that aren't able to have a huge amount of protein, whether leucine enriched sit feed or a product or a powder that would be practical or useful to use?
Yeah, I think there have been sort of moves to sort of understand more about, how you pack more for your punch, basically. And one way of doing that is there's a couple of ways. One is by minimising the as you say, the quantity in liquid or whatever form that they have to consume it in, or the other is by having an optimal quantity of amino acids. And if that means boosting the leucine concentration, then that would seem. But I must say as well, I have to be I have to be honest. We didn't switch leucine for something else. So ostensibly, maybe it is leucine. Maybe you put valine, it'll do the same thing, if that makes sense, as a branch chain. Sorry, I have to say that as well as a scientist. It's not the perfect experiment. I can stand back and say, given what we've done with leucine and everyone else done, if you look at the animal world of nutrition, no one feeds a rat or a mouse protein to understand about how an animal deals with protein or how a cell senses it. They give them leucine. So everyone has jumped on this, right? Sorry. Yeah.
I was just wondering, following on from that, whether there is a glass ceiling when you're looking at whole protein boluses that's effective, because I know you've got the window, but then is there a certain gram amount as well?
Yeah, there is. Good question. So, it's been done with some of the major sources, so soy whey casein, for example. And, it would lie in between, as it were, a high-quality protein. It would lie somewhere around 20 to 30 grams. Now, the other problem is nobody really looks at it in the context of grams per kilo, body weight, or even muscle. So it's really somewhere there.
So when you were looking, one of your studies much earlier on, I think had 48-gram boluses.
Yeah.
So the amount over that, say roughly 20 to 30 grams every 4 hours max, because we were talking about the time.
So around that would be, if you were to plan something, that would be what you would do.
The rest of it, when you talk about it goes peripheral, is that just going to be excreted, or are there other places that additional?
So the main sites are muscle and the liver, basically. The main, but of course every tissue is made up of protein. So but it's all based on the amount of mass and the rate of the turnover of that tissue. So the majority of the lion's share is going to go towards the muscle. Muscle is, if you measure, some people will be advocates of saying, I don't want to just measure muscle, I'll measure whole body, which you can do. So you can measure whole body protein synthesis and whole body protein breakdown. The two usually somewhat align, if that makes sense. And the problem with whole body is that it's coming from everywhere. So it's hard to know, if something changes, what's driving that change, if that makes sense. In terms of the 50 grams at the start of 48 grams, it was simply done at that time to provide a super maximal, because we wanted to push the system as hard as it could be pushed, and then said, how does that affect this sort of, clearly, if you keep eating protein, you don't look like Arnold Schwarzenegger when he was 25, do you? So, unfortunately, that doesn't work. So it would, if you think about it, why wouldn't the muscle just shut itself off, So it kind of makes sense, doesn't it, really, if you think about it like that. But, yeah, once the tissues are used, I can't comment on how, an individual tissue will use and the kinetics like I can in muscle. But what happens is, if you give a dose like that, it's really simple. The blood urea concentration just goes up. So you can start to see that it's going away from processes that are either using it for donating into the TCA cycle, for example, for carbon, or it's going to other sources like I said, mainly through excretion in the urine through urea, ammonia and urea production.
Thank you.
So you kind of as soon as it becomes kind of useless, urea starts to ramp up.